Thank you, Anatoly, for chairing this session, and thank you, Helen, for organizing this conference. I want to speak about the new generic carbon budget model, GCBM, and how we're applying it to quantify boreal forest carbon dynamics. I want to acknowledge the contributions of my co-authors, mostly from our carbon accounting team in the Canadian Forest Service, and that of Dr. Robert Waterworth, who is with the Mullion Group in Australia and a colleague in the development of the underlying platform. As we have heard by other speakers, net negative and net zero emission targets can only be achieved if we bring the land sector and in particular forests into play. This has led to an increasing demand from the policy and science communities for a better understanding of natural climate solutions that involve the land sector. But as we have shown in prior research, boreal forests are also at risk from climate change, in particular the impacts of wildfires. Therefore, our ability to quantify the impacts of forest management, natural disturbances, and climate change on future greenhouse gas emissions and removals requires that we develop and implement scientifically credible tools. This large increase in interest in the science and policy community about natural climate solutions has resulted in new needs for these models. It is very important that we develop the ability to calculate and quantify the difference between the actual natural climate solutions outcomes and the counterfactual or the baseline that would have occurred had the mitigation action not been implemented. It is important for us to understand that both of these estimates, the outcome and the counterfactual, contribute equally to the uncertainty about the actual impact of the mitigation outcome on the atmosphere, but that it is only possible to verify the actual estimate, not the counterfactual. This is perhaps not a big deal when it comes to issues like afforestation and restoration of forest cover, but it is a really challenging task when we try to address wildfire risk reduction, and where the counterfactual is the area that would have burned had the mitigation action not taken place. What we do need are spatially explicit integrated models that operate in annual time steps or better, that are informed by the best available data on forest inventories and time series of activity data and the treatment responses of ecosystems. Ideally, we should implement these models with spatial coverage across all land categories. In Canada, we use a system of models for the analysis of natural climate solution mitigation analyses that are built around the systems approach that was recommended by the IPCC in 2007. We have an ecosystem carbon model that is either the CBM CFS3 or the new GCBM that represents ecosystem carbon dynamics. We have a carbon budget model framework for harvested wood products with which we quantify the fate of the harvested material, such as biofuels and wood products of various duration of lifespans, and how their use achieves substitution benefits by avoiding the emissions from fossil fuels and other emissions-intensive products. The first two models in this framework are the ones that are used for Canada's National Greenhouse Gas Inventory reporting and for emission trends reporting. But the third one, of course, is not used for reporting because where substitution benefits occur in other sectors, these will be captured by the reporting in the other sectors. The carbon budget model of the Canadian forest sector, version 3, was started to be developed all the way back in 1989. It is an ecosystem carbon dynamics model that represents above and below ground biomass and the dead organic matter, woody debris, and soil carbon pools, and is fully compliant with the IPCC guidelines. It is the model that we use in Canada for national forest reporting systems. It is based on the IPCC gain loss method, which means we estimate an initial inventory and we then grow and lose forests through activity data and as defined by yield curves, etc. This allows us to make an attribution of the annual reported emissions to annual activity data, whether these are forest management, fires, insects, or land use changes. This approach also allows us to have a seamless transition between the reported past emissions and removal estimates and the projected future estimates. This ability of simply extending the activity data time series allows us to use these tools for emission trends reporting, nationally determined contributions, and natural climate solutions. We also have a framework for harvested wood products. I won't elaborate on that. And we use uncertainty analyses as published by Metzaranta et al. In 2017 to estimate the uncertainties both in the ecosystem and harvested wood products estimates. The model is freely available in 5 languages with documentation, and we provide training. However, one of the problems with this approach is that we have a very limited ability to process big data sets, particularly spatially explicit time series obtained from remote sensing on disturbances and recovery rates. We have therefore now started to develop the generic carbon budget model. It is based on the science modules of the CBM CFS3 implemented on the full lens integration tool, or FLINT platform, that we jointly developed with Rob Waterworth and his team in Australia. And that is open source, available on Moja Global's website. I provide the links at the end of the presentation. Moja Global is a not-for-profit organization under the Linux Foundation that was established to support the development of MRV systems around the world. The approach that we're implementing in Canada is spatially explicit. We have areas where we represent simulations at 30 meters resolution, others where we use 1 hectare. And we have simulated about 200 million hectares so far. We apply the model to both managed and unmanaged forests. The CBM CFS3 was only applied to managed forests. Because the model is open source and modular, it is much easier now to develop additional modules. And we have completed the implementation of a MOS module and a national peatlands model, the CAMP. Kelly Bona will speak about that later in this session. That peatland model has been applied to about 64 million hectares of peatland data at 1 hectare resolution. We're working with several groups, including Mathieu Fatin, who's also at this conference, on climate-sensitive growth and mortality estimation, excuse me, fire severity data from remote sensing data, and also on albedo. We're in the early stages of implementing improved forest inventory data and change data from the remote sensing time series that my colleagues in the Canadian Forest Service are developing. This modeling framework runs on workstations, computing clusters, or cloud-based. It's open source, and we're developing online training. The biggest challenge for projections is that we require spatially explicit data of future events and where the mitigation actions are implemented. This is, again, not a challenge when we deal with restoration of forest cover and afforestation. It is a challenge when it comes to forecasting where future wildfires might occur. The big advantage of having a spatially explicit framework is that we will be able to support the future monitoring of the outcome of natural climate solutions, such as the 2 billion tree program that was just launched in Canada. For those familiar with the CBM CFS3, you will remember that it uses inventory data, activity data on forest management and fires, etc., as well as a series of databases, ecological parameters, and growth curve libraries to represent spatially referenced information on carbon stocks, emissions, and removals. The GCBM is very similar in its approach, except that, and it uses some of the same infrastructure as the CBM CFS3, so transition is facilitated between the 2 modeling systems. But the important thing is that instead of having spatially referenced tabular information, all the information that is, or almost all of the information that is used by the model is spatially explicit, requiring annual time series of maps. And the model then generates results that are similarly spatially explicit and in annual time steps. Here's just an example as a visual demonstration of an example of the results for a region in the boreal forest of Canada. On the left, you see 1 time slice of disturbances, in blue the harvest, and in red the fire events that occurred in 2011 in this region. And we use these time series to drive the carbon dynamics that are represented on the right in the upper image as a map. 1 hectare resolution of the carbon stock changes in that particular time step. And in the bottom graph, you see the summary for that map, and you see the carbon stock increases in some years, but the progressively more losses, and particularly in 2011, where we had that big fire event in this landscape. So this kind of system now allows us to do all sorts of analyses. And I'll just give a few example applications. So first, an example in the oil sands region, where we applied the model to some 1.3 million hectares in Alberta, looking at the cumulative effects of natural and anthropogenic disturbances on the forest carbon balance over the period 1985 to 2012. This is work that was led by Cindy Shaw and was done collaboratively with various colleagues. And in the diagram on the left, you can just see the disturbance emissions directly related to the various land use activities and land use change activities. A second example, led by Carolyn Smith from our team, is the BC-wide analysis of natural climate solution opportunities. The model was run at 1 hectare resolution for all the 60 million hectares or so of British Columbia, and we included projections to 2070. In this particular study, we also had a fully integrated harvested wood products model, substitution benefits, and economic analyses that were added to the outputs of the spatially explicit GCBM simulations. And again, that paper was published in 2020 in Carbon Balance and Management. Just briefly, a couple of other examples. We worked with Ronnie Drewer and his team on a recently published paper on natural climate solutions for Canada. One of the 24 NCS pathways, that of afforestation and restoration of forest cover, was conducted at the national scale with the GCBM, looking at the various potentially afforestable areas and the consequences for the carbon balance. We also just published a paper with Georgina Magnus and others on the impacts of Forest Ontario's 50 Million Trees program. And with Tara Sharma and others, we're working on, we're just completing a study of the carbon balance of the forests in 31 national parks of Canada to quantify the impacts of conservation-based mitigation strategies, because Canada's national parks, of course, are the poster childs of long-term conservation. Just a sneak preview, what these results show is that despite the conservation efforts that have been going on for decades, these parks, unfortunately, are no longer carbon sinks. In fact, the cumulative carbon balance over the period 1990 to 2020, from a greenhouse gas perspective, is a small net source, largely driven by increasing wildfires in Western Canada, but also increasing insects. Because of the importance of wildfire impacts, we're also conducting research with the Pacific Institute for Climate Solutions on the impacts of wildfire and carbon, how we can increase forest resilience in Western North America by combining objectives of wildfire management and a bioeconomy for the benefit of greater forest resilience. Internationally, the model is applied to all of South Korea, and we have pilot projects in Chile and Mexico as well. So in summary, the GCBM is an open source modular framework built on the Flint platform of Moja Global. The development is ongoing. The model is already deployed for several projects in Canada and internationally. We are currently focusing various activities on improving the development of environmentally sensitive growth and yield modeling. Juha Metsäranta gave a presentation on that in session 10. The expanded application of the CAMP, the peatland model, will be presented later today in Kelly Bona's presentation in this session. We are improving the representation of forest carbon management activities, including the natural climate solutions and the assessment of wildfire risks and mitigation options. We're working on improving the representation of tree planting outcomes, including better quantification of the counterfactuals to support Canada's 2 billion trees program. And we're also working with the remote sensing community to better incorporate the remote sensing derived time series into the model. We have improved representation of wildfire severity. It's a project with Ellen Whitman at the Northern Forestry Center. Our goal is to use the GCBM in Canada's National Forest Carbon Monitoring, Accounting, and Reporting System to ultimately transition it from a spatially referenced to a fully spatially explicit system. And lastly, online training is under development. I thank you for your attention. The contacts for the model are myself and my colleague Max Fellows, who deals with the technical aspects of this. The GitHub source, GitHub link to the open source is on the slide, and so are sources of publications. Thank you very much for your attention, and I look forward to questions.
Hello. Thanks for the opportunity to present the results of our study for heterotrophic respiration or respiration from coarse woody debris and soil in an old-growth boreal forest. Heterotrophic respiration is a very important process in carbon cycling in boreal forests, but it's one of the least studied ones. It depends on temperature, moisture, and substrate characteristics, so physical and chemical properties of soil and down logs. We tried to study all these factors at the same time. The study was made in an old-growth boreal forest, mixed one, mesic site conditions, and the forest is located in the Republic of Karelia, Kivach Nature Reserve, middle boreal zone. We measured CO2 fluxes with a closed dynamic chamber method using repeated measurement series, and at the same time we recorded temperature, moisture, and such characteristics as bulk density of wood and bark, nitrogen and carbon concentration, and so on. For down logs, we used two methodological approaches. The first one, we placed the chambers on the top of down logs, and in the second one, we placed samples inside chambers in case of highly decomposed wood, and so that log couldn't support the shape, the structure. The forest was mixed, so it gave us an opportunity to compare the effect of different tree species on CO2 fluxes from logs. So we studied spruce, birch, aspen, and pine, and used the chronosequence of decomposition or different times since tree death, up to more than 60 years. So let's start describing the results from soil fluxes. Its variability was, first of all, due to microsite variation. The maximum fluxes is in the most rich forests, in herb-rich forests or Picetum herbosum, and minimum fluxes in Picetum myrtillosum oxalidosum. The share of microbial respiration was 80% from the total CO flux from soil, and about 20% was root respiration. During 2 years, we followed seasonal dynamics of CO2 fluxes from soil. Here, with the green line, we can see the CO2 fluxes from soil in the Picetum herbosum, blue color Picetum myrtillosum, and red color Picetum myrtillosa oxalidosum. Q10 varied from 2 to almost 4, and which is important, our study once again demonstrated the importance of taking into account a cold period when measuring CO2 fluxes from soil. In our case, these fluxes contributed on average 20% to the total CO2 flux from soil. And which is interesting, the differences in the temperature regime among macrosite types were the most pronounced during summer periods. So we can see it's June, July, August. For coarse woody debris, the fluxes were tree species specific and dependent on temperature, air temperature, or more specifically wood temperature. And another source of variation was related to the degree of decomposition. So decay class explain a lot in the variation of CO2 fluxes. Time since tree death increased from 0 to up to more than 60 years since tree death for pine and less for aspen and birch for deciduous tree species. And at the same time, wood bulk density and bark bulk density and mass decreased across decay classes. So here we can see how temperature sensitive is CO2 flux from down logs related to tree species. 0 means that the trees died in the current year, so the phloem is intact and the phloem is what is breathing. From decomposing logs, the most sharp curves and the most obvious dependence on temperature was for middle decomposed logs, decay class 2 and 3. And for pine, there was no dependence because of very heterogeneous decomposition process for pine. If putting all tree species together and calculating mass loss percent, so relating given bulk density to the bulk density of living trees, we get the following surface. So maximum flux was observed from wood mass loss percent 0, and then it is decreasing following the degree of decomposition of logs. The most sharp curves depending on wood temperature were observed for the least decomposed logs, and highly decomposed logs didn't demonstrate that obvious relationship with temperature. We used the component integration method for study the share of bark and wood in the decomposition of down logs. Bark constitutes more than 25% of tree volume for boreal tree species and something like 15% of mass, but its decomposition is quite poorly studied. From the point of view of CO2 flux, first of all, bark represents a physical barrier for CO2 fluxes, and on the other hand, it's breathing itself because it's decomposing. So in our case, our results show that the share of bark and wood in the total CO2 flux depends on tree species and the degree of decomposition. Altogether, down logs contribute on average 15% to the total microbial respiration in this ecosystem type during the vegetation season. To conclude, CO2 emission from soil depended on microsite variation. The mean share of microbial respiration was about 80%, and the seasonal dynamics depended on soil temperature at the depth of 10 centimeters. And the differences in the temperature regime among microsites were the most pronounced in the warmest period. The cold season contributed on average 20% to the total amount of CO2 emission from soil surface. The CO2 flux from down logs depended on temperature and wood decomposition status, and the trends in the dynamics of share on wood and bark in microbial respiration of down logs were tree species specific. The respiration from down logs comprised 15% from the total microbial respiration during the vegetation period. Thanks a lot for your attention.
Good. Yeah, my name is Anusha Satyanath, and I have worked as a postdoctoral fellow at Swedish University of Agricultural Sciences. And actually, I finished my postdoc 3 months ago. So I'm going to present the work I have done during my stay at Sweden. So the title of my presentation is Reconciling the Carbon Balance of Northern Sweden Using Measurements and Modeling. So the work is done in collaboration with Lund University, that is from the south of Sweden. And the background and objectives for the project. So we all know the boreal forest is an important component in the climate mitigation strategies because it is known as one of the biggest sink for CO2, but we still don't know up to what extent the boreal region contribute to the global carbon sink. Hence, it is necessary to provide the accurate accounting of carbon budget. So our study aimed to connect different carbon cycle observations to reconcile carbon fluxes and to estimate the carbon balance of northern Sweden. And our specific objectives for this project is to compare model estimates of fluxes and model estimates of concentration with available observations, and to determine how well the atmospheric concentration observations within the Nordic region can be used to constrain the fluxes in the Nordic region. We also try to investigate how fluxes and concentration compare during an extreme event like the 2018 European drought episode. So this is a schematic diagram showing a greenhouse gas emission assessment system from local to regional scale. And we have a similar eddy covariance system at Swadberget in the northern Sweden region. So it's a part of ICOS. ICOS is integrated carbon observation systems, and they have a lot of stations spread across Europe. So one is at Swadberget in this northern Sweden region. So we have any measurements at different levels of this 150-meter tall tower, and I have used the eddy covariance system that is mounted at 70 meters, so that have a larger footprint, almost 25 to 50 kilometers. Then coming to the materials and methods. So for we have fluxes and concentration. So for fluxes, we have observed fluxes and the modeled fluxes. So for observed fluxes, we used the eddy covariance observations from the ICOS tower I mentioned. So I have the eddy covariance system at 70 meters. It was initially at 60 meters, then it was raised to 70 meters. So it was then the eddy covariance system consists of anemometer and a closed path gas analyzer. It continuously measures CO2, water vapor, and the energy exchange between the boreal landscape and the atmosphere. And we get the measured NE, which is then processed following ICOS protocol and is gap filled and source partitioned into the flux components, gross primary production, and ecosystem respiration. So this is the observation available at the site scale. Now, for the regional fluxes, we have output from 4 vegetation models, and 2 of them are process-based ecosystem models. They are LPJ GUS and ORCID, and there are 2 diagnostic models. They are VPRM and SIPCASA. So I haven't run these vegetation models, but I took the output from these vegetation models. That means the vegetation fluxes, NE, GPP, and RECO. So this study is kind of a validation of modeled vegetation fluxes at the site and at the regional scale. And now coming to the concentration observation. So for the observed concentration, we have different ICO stations within the Nordic domain. So this is the map. And during our study period, that is from 2016 to 18, observations from 8 sites within the study domain were available. And they are high frequency CO2 concentration measurements, and they are available at different levels. And we use the one from the topmost level at each station. And the processed information is available through Global View Plus product. And now we have a transport model that is called the Lund University Modular Inversion Algorithm, LUMIA system, and that connects the fluxes to the concentration. So we used the modeled fluxes from the 4 vegetation models I have mentioned earlier as a biospheric input to the LUMIA system. Then the anthropogenic emissions are based on the EDGAR inventory. Then this LUMIA transport model, it has 2 components. The foreground component, that the foreground concentration is measured using the flux part footprints regional transport model. And for the background concentration, we use the TM5 boundary condition. Then we get the model concentration at each of these ICO stations, which is further compared to the observed concentrations. Now coming to the results. So we are comparing the fluxes at the Swadberget, that is at the local landscape scale. So here I am showing the time series of NE, GPP, and RECO in first figure for the period 2016 to 18, and from 4 of the models and compared with the observation. The observation is shown in green. So we can see in the first figure A, the modeled fluxes compares well with observation, though there are some discrepancies, like LPJ GUS shows a very large peak during 2018 summer, and VPRM and LPJ GUS showed near zero winter fluxes. And then we can see the process-based ecosystem models, that is LPJGUS and ORCID. They simulate higher GPP and RECO. And when we look at the cumulative plot of NE, GPP, and RECO in the plot on the right side, it is each column wise, it is the LPJ, PPRM, SIPCASA, ORCID, and eddy covariance data in the last. So what we expect is that 2018 being a drought year, it will have less NE uptake. But instead, here 2000 for the region Swartberget or for Swartberget station, 2017 had a lesser CO2 uptake even compared to 2018 and also to 2016. And that feature is not only noted in the observation, it is captured by most of the models except LPJGUS. And this LPJGUS behavior is due to this anomalous peak that we have seen in 2018. Now we are trying to compare the regional fluxes. So what we have seen is the comparison of fluxes at the side scale, and now we are going to see how much widespread the features seen at the side scale and how much the site can represent the northern Sweden region. So here in this, here I am showing the spatial map of NE annual budget. This for the year 2018. So the blue star shows the Swartberget location, and the region around it, we call it the northern Sweden region. So we can see in all of the 4 models, LPJGUS, VPRM, SIPCASA, and ORCID, they all showed the region as a carbon sink, but the sink strength varies from region to or model to model. But within the northern Sweden region, there is a homogeneous behavior. And in the plot on the right, we are comparing the again the NE annual budget, but separately for all the years, and for site and region separately. So all the models showed the site as well as the region is a carbon sink throughout the period, but the lesser sink is during 2017. And in LPJGUS, it showed as a small source, not on LPJ. SIPCASA, it showed as a small source in 2017. And now we are coming to the concentration. So we compared the fluxes and we used those fluxes as an input to the Lumia transport model. And that is a forward transport of fluxes to the observation sites. Now we have concentration derived using those fluxes. So here we are comparing those concentration with the observed concentration. So this is shown only for the Swartberget location. So we can see, though there are differences in the flux, we can see a better match with the concentration. And here we used all the hourly concentration available, daytime hourly concentration. So in the second plot, what we tried to do is that we filtered some of the concentration values in such a way that we have chosen only those hours when the site is, when the flux is really sensitive to the, or when the site or the concentration observation is sensitive to fluxes within northern Sweden region. That means in this map, you can see the region in purple color that we call the northern Sweden region. So we choose that concentration only when it is sensitive to the fluxes within this light purple region. When the compared to the total, so for that we use the flux part footprints. So when the footprint over the region is much higher than its total footprint, we considered it as a considered it and used in this plot. So in this second plot, you can see during those hours, there are times, there are peaks during which the concentration is purely influenced by the fluxes. So this is to show that we can further use these ICOS observations to constrain the fluxes within the region, maybe in an inversion framework. So the conclusions from my study, so we have established a framework for combining different observations, different fluxes and concentration observations, and also different models, vegetation and atmospheric transport model, to investigate the carbon balance of northern Sweden and to explore how representative the experimental site Swartberget is for the northern Sweden region. And we find that the northern Swedish boreal study region was a carbon sink for all the years, whereas model differed in sink strength, inter and intra-annual variability, as well as the response to 2018 drought. The different 7 modeled concentration when the observations are sensitive to northern Sweden proved the potential of observations to be used for refining the flux estimate further in an inversion framework. So our study overall highlights the need to further improve vegetation models through such model data intercomparisons and using inverse transport models. Thank you.
Many thanks. A lot of interesting things, and we have time for questions. At least one question. Who? I see, but I do not know who would like to put a question.
If not, we should probably move on.
No, currently I do not see. Okay, many thanks. Many thanks for very really interesting presentation. We will go ahead. Next presentation will be done by Lisa Scott. Floor is yours.
Hi, everyone. Hopefully you can hear me okay.
Yes.
Let me go ahead and, okay, great. Let me go ahead and share my screen. Let's see. Okay. Okay.
Okay.
So great. Okay. So I'm a graduate student at the University of New Hampshire in the northeastern US. I'm working with Merrick Petrick and John Gunn. So today I'm going to be talking about a decision support framework to assess carbon outcomes from a salvage or no salvage response following an eastern spruce budworm outbreak. So for some background information, roughly 4.7 million hectares of spruce fir forest are at risk of defoliation in the northeastern US from a spruce budworm outbreak. A previous study by Gunn et al. In 2020 used the forest vegetation simulator to look at about 5,000 forest inventory analysis FIA plots in the Northeast to model carbon outcomes 40 years after a spruce budworm outbreak under salvage and no salvage scenarios. They then tracked those carbon stocks into the forest product industry to account for avoided emissions post-salvage. So in general, what they found was that, as you'd expect, the management response of whether or not to salvage after a widespread defoliation event has major implications for forest carbon budgets in the Northeast. So to expand on that a little bit more, Gunn et al. Found that within the first 10 to 20 years following an outbreak, choosing to salvage typically leads to a net carbon emissions, so where these values are positive here. And then over longer time periods, salvaging eventually begins to store more carbon, largely driven by that regeneration response. So those findings help shape the questions for this study, where we're curious to see if there might be stand conditions where not salvaging may be preferred, and how economic discounting can be used as a tool to help decide whether or not salvaging is preferred, where discounting can potentially be used to place a greater preference on valuing those near-term emissions, that near-term storage, instead of having to wait longer time periods to begin sequestering more carbon. So just to briefly go over discounting, if we look at a monetary example of $100, a 0% discount rate, so $100 at a 0% discount rate would be equal to $100 40 years from now. As you increase that discount rate up to 5%, you're increasingly valuing receiving those benefits in the near term. So $100 is worth almost nothing to you 40 years from now. So if we take that, that concept and apply it to carbon, so here, again, we're trying to capture that valuing that preference for those near-term carbon savings instead of having to wait, where there's a greater uncertainty that the forest may respond in a way that will repay those initial carbon debts. So as we increase the discount rate to 5%, there's less of a difference between that salvage and no salvage response, and there may be more scenarios where you may choose not to salvage. So again, in this image, the positive values as we're choosing not to salvage stores more carbon, and the negative values as we're salvaging stores more carbon and is preferred from a carbon perspective. So looking at the proportion of plots, so we use the same FIA plots from Gunn et al., those roughly 5,000 plots in the Northeast. At a 0% discount rate, over 75% of plots choosing to salvage is preferred at over 75% of plots. And then as you increase the discount rate to 5%, a greater proportion is preferred for not salvaging as well. So it's almost a 50-50 trade-off between either choosing not to salvage or salvaging it at plots across the Northeast. So we created a lasso regression model with a number of stand conditions as predictors for the response of that carbon output from salvage and no salvage scenarios. And we had a large number of input features, 81 features based on spruce budworm host species, so balsam fir and spruce species, and their basal area, size, stocking, and then a number of more general site characteristics like elevation and slope. And the lasso model is a shrinkage model, so it will choose only the most important features out of those 81 predictors used to identify our differences in carbon as the response variable at year 40. So our carbon values, we had a number of scenarios, or 0 to 5% discount rate scenarios. And then these treatment scenarios here, those are actually the residual stand conditions. So what the stand looks like at year 0 when an outbreak occurs. So for example, if a heavy cut had previously been done, then there's not going to be a lot of volume to salvage when an outbreak hits. If no management had previously been done, then there's likely going to be more volume that needs to be salvaged in that scenario. So the lasso model takes these predictors and figure out which are the most useful for predicting our carbon response, and then what are the relationships between those predictors and our response. So our results, so here the positive bars, those are the models, the scenarios where the lasso is more useful and provides a carbon savings compared to always choosing to salvage log. So here you can see those residual stand conditions, the moderate to no management are where the lasso model, so again, those are the scenarios where there's more volume to salvage because more volume has been left there at the start of an outbreak. So the lasso models are more useful in those cases compared to a heavier, clear cut where there's not going to be a lot of wood to remove anyways. And then also as the discount rate increases, so in those higher discount rate scenarios where you value those near-term emissions more, the lasso models are also more useful in those scenarios because as we saw earlier, a greater proportion of plots are no salvage plots in those scenarios as well. So looking at our most important coefficients, the lasso models chose 9 out of those 81, where our diversity parameter, Simpson's diversity index and site index were the most negatively related to no salvage. So we expect our no salvage plots to be less diverse and have lower site index values. And then on the other end, our other hosts are spruce species basal area and our balsam fir quadratic mean diameter. We expect those values to be higher on no salvage plots. So there's also, these models can also potentially be applied at a finer scale using 2 methods. So a rule-based application, which is just kind of a quick checklist to go through and see if your stand conditions match each of these conditions, then not salvaging is recommended. If you answer no to any of these conditions, then you can double check with the equation that the lasso model outputs before deciding whether or not to salvage. So here's the example of the rule-based application under a moderate harvest. So a moderate amount of wood that needs to be salvaged at a 3% discount rate. If you check yes to each of these stand conditions, then not salvaging is recommended. If you check no to any of these, then you can double check your values in the equation before deciding to salvage. So then here's the equation that's put out by the lasso models, where again, if you check no through the quick checklist, you can double check your values here. If the value is greater than 0, then not salvaging is recommended. If it's less than 0, then salvaging is recommended. So to wrap things up, in general for stand characteristics, the size and amount of host species is important for salvage decision making. So a higher quadratic mean diameter and basal area could suggest not salvaging may be preferred. Less productive or diverse sites, so those smaller Simpson's diversity index and site index values could also suggest not salvaging is preferred because those sites may not respond as well or as quickly in a way that will repay those initial carbon debts from salvaging. In terms of discounting, a higher discount rate or the more that you value storing carbon in the near term within the first 10 to 20 years could suggest salvaging less often may be preferred. And especially in those situations where there's more volume that needs to be taken out. So those moderate to no management residual conditions that we looked at. And then in general, the greater the volume that's removed from salvaging, the greater the swings in the carbon budget and the greater the risk that those carbon debts aren't going to be repaid. So if greenhouse gas emissions is a primary management objective, and there is a lot of wood to salvage on poor sites or sites without a lot of advanced regeneration, you could choose to salvage less or not salvage. And I think that's it, if there are any questions.
Yeah, many thanks. Interesting topic, interesting view. We do not often see similar consideration in our conferences, and we have time for questions.
Okay.
Anatoly, if I may, just one quick question, Lisa. Thank you for an excellent presentation. Another factor that determines the outcome of the salvage logging decision depends on how the wood is used. I was just, while you were talking, looking at the Gunn et al. Presentation, and it looks like they do include harvested wood products and bioenergy, which is great. But you didn't consider in the model how changes in the wood use might also determine your outcome, or is that something you have looked at?
That's a great point. Thanks for bringing that up. We didn't use that specifically in this model. I think because we thought that was accounted for it in the Gunn et al. Study. But you mean how the salvaging response may, those carbon outcomes from salvaging may vary based on how that, so a range of salvaging conditions instead of just salvaging. Is that what you mean?
The same salvage, but different wood uses, because how you use the wood determines how quickly the carbon is released to the atmosphere. If you use more for bioenergy than for long-lived products, you have a greater carbon debt in the short term, for example.
Right. Okay. Yeah, that's a great point. We didn't look at that for this, but that would be interesting to to try it in a next version. Thank you.
Yeah, many thanks, Lisa. We will go ahead. Next, we have a poster presented by Samantha Miller. 5, maximum 6 minutes. Understand, because we understand that 5 minutes is really not enough.
All right, let me just share my screen.
And we can hear you just fine, Samantha.
Okay, great.
Okay, we can see. Yeah, you're all set.
Okay, perfect. Thank you for attending my poster presentation about model selection for litter decomposition in Alaskan boreal forests. Decomposition is a major component of carbon balance, and decay rates derived from exponential models are frequently used in global carbon cycling models. However, the traditionally used single pool exponential decay model has been widely criticized, and more recently, a Weibull model has been proposed as a more flexible alternative. So here we compared these two models fit to mass loss data from litter bags deployed in 2 common boreal forest types in interior Alaska, black spruce forest and Alaskan paper birch forest. And the litter bags contain 3 common litter species, birch, spruce, and a mixture of feather mosses. So we sought to answer 2 main questions: which decay model best describes litter decomposition in boreal ecosystems of Alaska? And 2, how does model selection affect projections of litter mean residence time and ecosystem level litter turnover? So we found that the Weibull model best describes boreal litter decomposition, but both models produce similar estimates of litter mean residence time. However, I want to point out that there's a large degree of uncertainty with moss mean residence time, and this is because moss decomposes so slowly that we have not captured the majority of its decomposition trajectory even over 5 years. Finally, we found that while both models estimated slower ecosystem level turnover in spruce forests, the Weibull model estimate was slower than the exponential model. We also found that moss and not dominant tree species is the main driver of differences in litter turnover between these forest types, which further highlights the need to improve our understanding of moss decomposition. This work adds to a growing body of research that suggests that the Weibull model is a more suitable model to apply to a diverse range of litter decomposition trajectories, including variable and slow decomposition found in boreal forests. Incorporating parameter estimates from the Weibull model may be able to improve regional and global carbon cycling models by more accurately representing litter decomposition. And with that, I'd be happy to answer any questions if we have time.
Many thanks, we have time. You have excellently managed your presentation. Questions?
I have a question, Samantha.
Mm-hmm.
So on your mean residence time, there's a lot of error associated with moss mean residence time in the spruce forest, but not as much in the birch forest. Do you know what's going on there?
That's a good question. I'm not sure what's going on there because they look kind of similar. I think, yeah, I don't know. That's a good question. I think in general, it's like difficult to trust the moss decomposition because we only get to like 80% mass remaining. So not very much has decomposed. So we just really don't have an idea of what the trajectory will look like. So it's just pretty inaccurate.
Thank you. One more question.
I have another quick question. Well, first of all, I just really appreciate this study, and I've been trying to model moss decay for a while, and I understand the challenges. But something, just a really simple question for the birch and the spruce litter, was this like needles, like, or was it like wood litter?
No, it's foliage litter. So needles and then leaves.
And leaves, yeah, that's right.
Yeah.
All right, thanks.
Yeah.
Do we have more questions? Many thanks. Many thanks. Good presented. The next we have next presentation, Melissa Lucas from Alaska. Complicated question about system approach to forest life.
Okay, we can see your screen, Melissa. And yes, perfect. Yeah. Awesome. And we can hear you
too?
Yeah.
Okay, sorry. Thank you, Anatoly, for organizing the session. Thanks to everybody for coming. It's only 7 a.m. here, so it's a little early. Thanks for the people. Oh, in Alaska, it's even earlier. So I'm going to be talking about some work that was an interdisciplinary collaboration. I'm going to be talking about work where we looked at fire, vegetation, soil, and hydrology, and how it affected carbon dynamics in interior Alaska. And this work is an interdisciplinary collaboration between myself and my PhD student, Shelby Weiss, who are more on the forest ecologist side of things, collaborating with 2 hydrologists, Adrian Marshall and Tim Link, and 2 permafrost experts, Dmitry Nikolsky and Vladimir Romanovsky. And this work that I'm presenting is part of a much larger project funded by NSF that we call Reburns Alaska, that has an even larger suite of researchers involved in the project. And as many of you know, Alaska is a beautiful place that's warming at 2 to 3 times the rate of CONUS. It's a fire-adapted, fire-driven ecosystem, and the number of fires has been increasing in this ecosystem, and in the 3 to 5% range per year. And with those increasing fires come the opportunity for more of the fires to overlap, what we call reburns. And with the increasing fire rate, that you're actually oftentimes, well, at times you're having these short interval fires where there's really short times between these fires. And And we've known for a while that reburning leads to declines in conifer regen by Jill Johnstone's classic work. And our project was trying to look at, sort of use her research as the foundation, but then looking at those 3-time burns. So MTBS started in what, 1984, 85. But now with 2021, we're able to look at those 3-time burns in the MTBS data set. So sites where we had 3 overlapping burns with only 15 years between each fire, and then go to those field sites and measure their conifer regen. And we're indeed showing that that a 2-time burn is not the same as a 3-time burn, that even in the 3-time burn, you have an even greater decline in conifer regen. And Kate Hayes, some of you probably caught Kate's talk earlier this week, where she talked about her biomass and results as well. And I'll just, for those of you who missed Kate's great talk, I'll just talk about her work as part of the project, which is focused on this red area here in the Dalton. We also measured an area over the Stees, but just showing that, you know, it's one thing to see that data that shows the declines in conifer regen, but it's also visible all across the landscape as well, where those unburned sites here, the mature black spruce forest, and then you have these 1-time burns, lots of conifer regen there, quite a few snags. But once you get to the 2-time burn, large increase in percentage of rock, open canopy, huge deciduous component here. And then in those 3-time burns really dominated, as you can see, by the aspen. And we wanted to, when we did this field work as part of the project, we wanted to make sure we captured those relationships that we determined in the field in our modeling work that was also associated with the project, and really try to see how those reburns played out on our landscape over the long term and under climate change. And so when we started this project, we wanted to make sure that we were capturing vegetation trends and moss and soil. I always like this picture of Jason Shabaga. Jason gave a talk earlier in the conference about soil respiration. I like this talk, it makes it look like Jason's telling these middle school students to worship soil, which I always think is appropriate in the boreal forest. And we wanted to also capture permafrost dynamics. And so the goal of this project was really to bring all these different components together in this integrated modeling framework, so we could look at these questions about feedbacks between fire, vegetation, hydrology, and permafrost. And so we started with Landis 2 as our sort of foundational model. So for those of you who aren't familiar with Landis 2, it's a spatially explicit model. So it makes maps. It's a process model that also is spatially interactive. So these cells talk to one another. So you feed in maps of fire ignition probability, like from the Karen Short database. And then based on that probability of ignition, you might have fire spread to a neighboring cell. So it's spatially interactive. And whether it spreads is of course dependent on daily fire weather index. So temperature, precip, wind direction, wind speed that you all feed into the model on a daily time step. And then whether it spreads is dependent not just on fire weather index, but also fuels. And Landis 2 is a model that operates at the species level. So although my little map here shows conifer and deciduous as depicted for simplicity's sake in a diagram, it really does simulate individual species. So it's a cohort model. So you specify in each individual raster cell whether you have black spruce or white spruce, or do you have aspen or birch. It simulates all the different species, all the different age cohorts, and tracks them over time. Oh, I could say a lot more about Landis, and fire, but basically we use that species, spatially explicit vegetation and fire model. And then we pulled out the previous soil carbon and nitrogen model that was in Landis, which was the original Bill Parton soil century model, and instead inserted in DAM MC-NIP, which is Rose Abramoff and Adrian Finzi's model of soil carbon nitrogen dynamics. And we wanted to use this one because it the soil pools that it simulates within that model are actually measurable soil pools in the field, like microbial carbon is part of the soil carbon modeling. So inserted that in. And then we also pulled out the soil bucket model that was in Landis and replaced it with a full hydrology and heat balance model called Shaw Simultaneous Heat and Water Transfer Model. And I'll just say that Shaw is a full hydrology model. And it's user defined in the sense that it estimates heat and water balance at all these different nodes through the canopy and then through the soil profile, and you can determine how many nodes you want. So I think we have about 30 nodes where it measures soil moisture in the soil profile, the rooting profile, and then another 20 below the rooting profile. And Shaw is able to measure soil depth, so we can compare snowpack measurements. It also does heat and water and captures differences in aspect, so you can look at how aspect affects snow depth and compare that to empirical data. And then it estimates a whole suite of parameters like evapotranspiration and runoff, snowmelt, transpiration. And this work as part of our project has already been published by Adrian Marshall, who's new a professor at Colorado School of Mines, and has still one paper that's upcoming on the ecohydrology side in Alaska on our project. And the final component that we added was GIPL, which I always think of as the gold standard of permafrost modeling with Dmitry and Vlad. And as you can see here, GIPL simulates soil temperature at all these different nodes within that soil profile of Landis. So snow, moss, litter, soil, and permafrost. And I think we have about 75 soil nodes within the permafrost. Probably more like 90. And then you have maybe 30 within the profile of the rooting profile of the vegetation. And so this is sort of this labor of love to try to build this model, and maybe a labor of frustration about how challenging it is to really take models that are computed in R and Fortran and recode them all into C# and bring them all into one integrated framework that allows us to look at feedbacks between vegetation, soil, and wildfire. And so I'll just show you just a little brief smattering of sort of how well the model performed. We basically calibrated the model and validated it at 3 sites. The top one is a permafrost site adjacent to, maybe it's actually on UAF campus technically, Smith Lake 2 that many of you know, and then 2 Bonanza Creek sites that probably many of you worked at. So here's the Birch site, and then here's a Burn site. And the thing to pay attention to really is just that the modeled results from our model, which are the dotted lines, are quite similar to the observed, the empirical field data, which are the solid lines. And we measure different depths, so they're not comparable between the sites based on the available empirical data. But you can see we're tracking soil moisture quite well in the model. And that's true of soil temperature too, those same sites, again, just trying to compare the solid lines and the dotted lines. And indeed, throughout those different depths, we're simulating the annual and diurnal trends quite well, or seasonal, sorry. So I'll just present some brief results, some preliminary results from a paper that we're working on here. We're doing a 12 million hectare landscape in Alaska, but I'm just going to show results from a really small area here in red, which is just sort of the surrounding area of Fairbanks, because we wanted to be able to capture those 3 sites there that we're using for calibration around it. So Smith Lake, here's the Birch, and then here's the Burn site. And what we found was that soil moisture was not very different between sort of a no climate change scenario, the gray one, historical climate, so 1970 to 1990. So the no climate change and climate change weren't very different. in their soil moisture, but quite different, as you can see on the right here, between the conifers on the left and the hardwoods. So hardwoods have much lower soil moisture, which would obviously have implications for, you know, when we're projecting these shifts in vegetation type across the landscape. So maybe integrated across the landscape might not be different, but obviously it'll be spatially different across the landscape based on forest type alone. We'll also be looking at changes in permafrost. This one here just shows sort of surface permafrost, the top 6 meters. My next round will be going down to the 75 meters down into the profile. And so for those of you who are familiar with this area of the Greater Fairbanks know that we're underestimating the permafrost here because I'm just doing the superficial. So I'll be redoing this one, but just to show you an example of how the model allows you to make maps of current distribution of permafrost, how it might differ in the future under no climate change, and then how it changes under NCAR climate change scenario. Our preliminary results show that under climate change, that indeed above ground carbon declines across this landscape. Keep in mind that historical is fairly increased a little bit flat. Keep in mind that this is the surrounding Fairbanks area, so not a huge amount of fire in this particular landscape. So this might differ at our larger landscape where we have a lot more fire. Also ran the model turning off different factors to try to get a sense of what was really important in driving above ground carbon trends. Soil moisture seems to be the winner initially, lots of blue here explaining about 70% of the variation, but that over time in the future under climate change, that soil temperature actually becomes quite important in driving above ground biomass trends. The real heavy lifting of the model application and feedback work is driven by my PhD student, Sylvie, who's probably in the audience today. And Sylvie, she's working on a paper now about future fire regimes under climate change in this landscape here in the sort of upper left. And then she'll be also working on some modeling work associated with how climate change will affect shifts in species biomass over time. I'll be working on a soil carbon paper next. And then I'll just end by putting in okay, I just wanted to put in a plug for the broader impacts that we're doing as part of our project. So if you know any kids or teachers, we're developing curriculum about boreal forests. That'll be publicly available. So if you had some teacher friends that you wanted to pass on our free curriculum to, feel free. It's starring famous movie stars like Brian. And I wanted to just end by thanking everyone working on our project and what a joy it is to work with these collaborators. Thank you.
Many thanks, Lisa. To see a real modeling cluster, what is very difficult to manage. Unfortunately, we do not have time for discussion, and we have to go ahead. That next speaker, Kelly Ann Bonham, again from Canada. Something interesting about Canadian peatlands.
We can see your slide.
Okay, great.
And we can hear you.
Whoops. Sorry, I'm having a bit of a weird thing going on with my screen, even though you guys can see me. Let me see. That's not on screen. Okay, just a minute. Okay.
We can see your slide.
You can see it? Okay,
yeah.
So I'll just, okay. Okay, good morning. I'd like to start by acknowledging my co-authors at the Canadian Forest Service. And because we don't have a lot of time today, I'm just going to jump right in. So peatlands cover a very large portion of the boreal forest here in Canada. As you can see from the map here, the green areas are the peatland areas, and about 80% of this is forested peatland. I don't have to convince you that peatlands have a high capacity to store carbon and also sequester carbon. It's generally accepted that peatlands store or sequester about 0.2 to 0.3 tons of carbon per hectare per year. And so given these conditions, Canadian forested peatlands have the potential to sequester about 1.2 million tons of carbon annually, but we know that these conditions are changing. So the objective of this study was to look at peatlands at a national scale level. Because I work for the Government of Canada, my mandate is on the one hand to build greenhouse gas emission and removal quantification tools in order to inform things like greenhouse gas reporting requirements, government initiatives that are aimed at conserving or enhancing carbon sinks. On the other hand, my objective of this study was also to build our scientific understanding of the impacts of climate change and how these might be impacting carbon sequestration rates. And in this talk, I'm going to really be focused on forested peatlands, since this is about the boreal forest, and specifically how shifting fire regimes might be impacting these rates. Okay. So in Canada, the carbon budget model of the Canadian forest sector is used to model greenhouse gas emission and removals on managed forest land for the purpose of national greenhouse gas reporting. So for the past 10 years, I've been working with the carbon accounting team at CFS to include moss-derived organic soils, in other words, peat, to this model and to the new generation of the model GCBM, which Werner spoke about earlier on in the session. Hopefully you were here for his talk. So I built a moss module for my PhD, and then went on to work with them to build this peatland module, which we call CAMP, which I will now get into more detail in. So the CAMP module works within the generic carbon budget model. So this was, as Werner had mentioned earlier, built on the Full Lands Integration Tool, or FLINT, and this was jointly developed by experts in Australia and the Canadian Forest Service. It's open source. Werner provided the GitHub link in his presentation at the end. What's interesting about this tool is it's spatially explicit. We can put it pretty much at any resolution that your computer has the capacity to run. It works in annual time steps, and it can be, for the CAMP model, we made sure it was nationally applicable to 9 different peatland categories. And these were the intersection of wetland type and tree cover type. So quickly, this is a really simplified version of what the CAMP model keeps track of. So the model tracks the growth of live biomass with different vegetation layers. And then these are turned over into litter pools, and the litter decays as a function of a Q10 relationship with mean annual temperature. Then this is eventually turned over into peat pools, which also decays. And then we also track water table depth. And water table depth is based on an empirical relationship with drought code index. So Drought code is an index developed by the Canadian Fire Weather Index System, and it was really useful here because we could obtain annual spatial layers of this drought code index. And then the other spatial layers that we were able to apply would be the fire map of Canada, and also the mean annual temperature, and then the drought code, as I just mentioned. And then we also apply a fire disturbance matrix. And this is essentially the proportion of carbon. So the matrix defines the proportion of carbon that is either emitted to the atmosphere or transferred to the dead pool as a result of a fire event. So in this study, the objective was to test and evaluate the national scale estimates of greenhouse gas emission and removals for the CAMP, and to compare the past or observed rates with present or modeled rates of carbon sequestration. And one of our hypotheses was that potentially these increased fire risk, what we were just discussing in some of the other talks, may be actually reducing the long-term carbon sequestration rate of these forested peatlands. So we ran the model between 1990 and 2018 for 63 million hectares, and the peatland map was at a 250 meter resolution. We're probably updating that to 1 hectare soon. Most of this land is forested peatland, as you can see here on the map. So all the green is essentially what we would class forested. The results were interesting. So first of all, we found that between 1990 and 2018, so the entire span here, we found that on average, the peatlands were actually a small source of carbon of about 0.13 tons of CO2 equivalent per year. So this was the modeled emission. And interestingly, though, if we took the time frame between 2000 and 2009, which you can clearly see here, and between that time frame, we saw what we would expect or what a normal fire pattern would be. So we still had fires, but it just wasn't extreme. So we essentially looked at that to exclude some of the more extreme fire events that we had in Canada. And if we look at that, we get a net sink of 0.34 tons of CO2 equivalent per hectare annually. And then when we look at this in comparison to flux data, a recent publication of flux data across Canada predicted basically a very small sink or almost neutral of a rate of 0.096 tons of CO2 equivalent per hectare per season. So we have to be careful when we're comparing flux data because this is seasonal, so we're not including winter emissions in this, and this does also not include fire emission. So we wanted to look at this a little bit closely. So instead of looking at as emission compared to flux rates, I also wanted to look at this in terms of the carbon sequestration rates and comparing this to some of the more long-term rates. So the carbon sequestration rates that we modeled between 1990 and 2018 were 4.7 grams of carbon per meter squared per year. And if we omit extreme fire years, again, this rate increases to about 12.9 grams of carbon per meter squared per year. But this is still much lower than the rates that we generally expect for peatlands, which is generally cited as 20 to 30 grams of carbon per meter squared per year. So I went back into the literature to see, you know, maybe these rates are changing. It's possible that these rates are getting smaller. We're seeing more fires. It makes sense, right? So I found a recent paper from a group in Canada from UQAM, and they cited a rate of 15.9, and they specifically look at forested peatlands, which generally would burn more frequently because you have trees to burn, right? So, so they found a rate of 15.9, a range of 9.3 to 22, and they observed, as you would expect, that peatland, so they're looking at peat carbon dating, that peat profiles with more charcoal would have lower rates, right? So given all of these, given some of these results and this new paper, essentially, I'm seeing that this is suggesting that the shift in national fire disturbance regimes are reducing forested peatland carbon sequestration and thereby potentially reducing Canada's national peatland carbon sink capacity. I wanted to give you another just quick sneak peek at the regional differences here. So this is actually, so the graph on the left is a comparison of net ecosystem exchange. So these are comparison of flux rates, and this does not include fire. So this is really just the net ecosystem exchange of CO2 within the systems. We're looking at modeled versus observed. Anything positive here would be a source. Anything negative here is a sink. So you can see that the observed flux rates from flux tower measures are highly variable, sometimes positive, sometimes sources, sometimes sinks. We expect those to be quite variable. They're on a different temporal scale as our modeled values. So we have to be a little bit careful about our comparison here, but I think it's still worth looking at. So essentially they're on a different temporal scale. So our modeled values here are averaged across 29 years. So they're really more long-term rates where we would expect that if we do not include fire, they should be sinks. They should all be pretty much sinks. That's what we expect. But the flux data is a little bit more variable because they're taking daily or seasonal rates and then converting them to annual. But when we look at the observed to modeled graph, which at first glance looks like the model might be doing a pretty poor job. But again, if we use our common sense, because again, these are flux rates, so again, more variable, but the model is still showing the same pattern, the same regional pattern. So based on the observed data, we would expect that the boreal plains would be a stronger sink than, say, the Atlantic maritime region. And the model is actually showing that same pattern. It's just that in the long term, all of those regions are sinks when we do not include fire. All right, so for future steps, we're currently running an uncertainty analysis. We're always trying to improve on the model. We're integrating anthropogenic disturbances like oil sands region disturbances. We're also looking at working in peak temperature and just spatial inputs and the ways we can do that. And then we'd like to also build a permafrost module. This is why we did not include some of the northern regions in our simulation, because we don't have permafrost dynamics yet, and we know that these are extremely important. So we're looking at including those as well. So thank you very much. And I'd like to open it to questions if I have time, and look forward to some discussion at some point.
Yeah, many thanks. Many thanks. Very interesting. Excuse me, my short question. In wetlands which you investigated, what is average fire return interval?
Oh, that's a good question. So we have fire return interval maps. So I don't know what the average would be, the national average.
Yeah, that's very specific.
Like, it's specific to each region, but it varies, between, what you would expect.
Why I'm asking, because we have in boreal zone really serious heat waves.
Mm-hmm.
And unfortunately, that's not usual for future science to consider this question. Many thanks. We have to go. That next presentation, Boris, excuse me, either Tupic or Tapek, I do not know. Excuse me, soil carbon models, yeah, environmental modifiers. Very interesting, welcome.
Okay, thank you, Anatoly. Yeah, it's actually Tupic. I'm originally from Slovakia, and it's kind of special Slovakian letter. Sorry for that. So thank you again, and thank you organizers for this opportunity, and hello everyone. On behalf of me and my colleagues, I will present our study that actually aims to. Okay, do you see my?
You need to share your screen.
Yeah.
Or do you want me to go through your slides? It's up to you.
No, I think it should be fine.
Okay.
I just can you hear me now?
Yeah, and we can see my face, your screen.
Very nice. Okay, so it will be there in a second.
Awesome.
Okay.
Yeah. Thank you, Boris.
Great. Okay, thank you very much. So yeah, as I mentioned, this study is on behalf of also my colleagues from Natural Resources Institute, Finland. And the title is Environmental Modifiers Designed for Soil Carbon Models for Mineral and Organic Soils. And previous excellent presentations on soil carbon modeling, not only soil carbon, but also biomass, have, for example, focused on differently on forests or peatlands. And my question for you, I was a little bit not so quick to ask during your presentations, was that are your models applicable only for these land uses, or can you have like a one simple model that can simulate peatlands and mineral soils together at the same time with some modification? So you can think about maybe answering this for me later, but this presentation a little bit should provide some sort of answer, because for this answer we were looking for in this study. So a lot of introduction, but I think it's good. The accurate estimates of changes in largest terrestrial carbon pool are needed for simulating their feedback to warming climates. And when you see, for example, these different models on the right, and these are like estimates on global scale compared to like global level data on the left, you see, for example, for this data, the most carbon is in boreal zone for peatlands, for example, and there is quite large spatial differences between these models and this data. And now we ask like, okay, so what could be the reason for this like a lot of models and a lot of spatial differences? And there is a theory that many soil carbon models have similar representation of carbon transfer in carbon pools. So the carbon is changing over time. It depends on the liter input, and then there is like a representation of the transfer in the pools or outside. And then there is some kind of modifier that is environmental function. Usually it is scaling default decomposition rates and CO2 emissions of this based on the model structure. And usually it is based on temperature and water content of the soil or air temperature or precipitation, as we have heard before. And I'm not sure if this is so clear, but soil carbon models usually differ in the representation of this, how this function is modifying the default decomposition rates, and they differ a lot. So you can see that there is some exponential increase, for example, for temperature, and there is like a lot of different functions for moisture. So some of them are bell-shaped, some of them are saturating, and some of them are linear. But in theory, we know that based on oxygen and substrate limitation to microbes, there should be some limitation when there is dry conditions to microbial activity and decomposition, and during wet conditions, okay, in dry conditions there is limitation in solute transfer, and in wet conditions there is limitation to oxygen, to gas, and then there is some conditions in between when the decomposition is optimal. So it's not very difficult. It's just if you think that this function should be something like bell-shaped, if you think about these differences in conditions, but still there is a lot of differences here. And then we can ask why there is so many differences in this model, and can they be applied globally? So we aimed here to design the environmental function, or adopt, maybe not design, because we adopt one after all, based on the theory of substrate and oxygen limitation on microbial respiration. And this function should be widely applicable for both well-drained mineral soils, so forests usually, and frequently water-saturated organic soils in boreal conditions, so peatlands or forested peatlands. And we also, of course, wanted to calibrate these functions with data represent as wide range of conditions as possible, and using Bayesian data simulations and IIASA soil carbon model. We apply this function in IIASA soil carbon model. It's similar like Century type of. So if you are familiar with Century, then let's think about the structure of Century. It doesn't matter so much. So the data from for this calibration, we used data from boreal forest Meyer ecotone. Basically, ecotone means that it's like connecting conditions of forest and Meyer. So there we had like 9 sites in Finland on the slope that some of them are on well-drained soils and going down to peatland. And for example, hydrological conditions, they are reflected by biomass. So previously also we have heard that moisture hugely affects the biomass growth. So there is, for example, look in these middle pictures, and then these are like hemispherical pictures of the tree stand, and more light there is, less trees there is. So for example, this is peatland, and almost everything is bright, so there is very little trees, but somewhere in the middle there is like best production of trees, and the stands are most productive and dense. And then when you go to the top to very dry conditions, then there is again some limitation and some more light in the canopy. And when looking on the soil profile data, then we can see that thickness of organic horizon is increasing also from these well-drained forests to peatlands. So darker these images, there is more carbon. So more carbon in peatlands than in like a lot of more, like 10 times or more than in upland forests. So this was already established that soil organic carbon in forests forms some kind of gradient to peatlands, and of course this is also something that is intuitively known, and this very well correlates with long-term soil moisture conditions. Okay, so this is quite simple data, but it is not very so often shown in the data. But on the other hand, soil respiration doesn't show some correlation, some increase with moisture. There is quite a lot of variation in all these sites. If you look of soil respiration measurements of forest transitions and Myers plotted, these are like instantaneous, let's say, representing 1 hour measurements, and they are plotted in the space of the soil water content in the landscape. So in this site we have like quite unique conditions, because we are considering very dry soils. There are like about 10 or sometimes even below 10% of soil water content, up to 90%. And so this will be very dry conditions or drier conditions for forests, and then wetter conditions or saturated for Myers, and then there is some transitions in between. So now we don't talk about individual forest types, but just like forests, transitions, and Myers. Okay, and so yeah, this is a very simple approach, and I'm also not sure why it has not been done before, but basically we took from literature this Davidson et al. 2012 Michaelis, it's the DA like DAM model, so dual Arrhenius Michaelis Menten function or model, that can be also represented by quite well by this very simple empirical function that is basically bell-shaped function of soil moisture and exponential function for soil temperature. What is surprising in this study really is that when you calibrate for large amount of soil water conditions, so when you really include mineral soils and peatlands together, so not only like mineral soil forests, then there is the optimum is somewhere in drier conditions in mineral soils, and there is very little sensitivity. So for example, dry conditions here don't affect so much landscape carbon balance. So this is the key, like we are not talking anymore about the site, but when we talk about like globally what is the landscape carbon balance, then this carbon in mineral soils doesn't make so much in the landscape. That's why the sensitivity to dry conditions or wet conditions is not like so big, but okay. But optimally, carbon is decomposing fastest in these conditions. I'm a little bit losing the mouse. When we go to increasing moisture conditions, then is it 11 minutes? Oh, okay. Sorry, I'm talking too much. Yeah, so let's just talk about this function then. Yeah, so for increasing moisture conditions, then there is like quite rapid decrease in these modifiers. So meaning 1, we have the default decomposition rate, and going to further, we reduce exponentially or linearly. Temperature functions are exponential. So this is just an example of how these functions look when they are combined. And I think I can just show this part, that when we take original functions for IIASA model for soil organic carbon, then this cannot be used for organic soils. But the function that is calibrated for the whole gradient performs quite well. And on the level of carbon dioxide emissions, both functions surprisingly perform quite well. And if we use for calibration only mineral soils and then use it for landscape level carbon stock estimate, then those will be heavily overestimated, and that's why they cannot be used. So that is known. So we have showed here improved predictions with very simple approach for soil carbon stocks and CO2 emissions. And this works only when the whole landscape level soil moisture is taking into account, but failed only when very narrow range for mineral soil is used, and also this needs to be tested. Thank you very much. I hope there are questions, but I think I exceeded my time.
Yes,
sorry.
So I'm taking over. Apparently, Anatoly has a technical issue, so hopefully he's going to be able to join back very quickly. Thank you very much, Boris. Again, if you have a question for Boris, please use the chat box. If not, then we'll move on to the presentation by Mathieu Fortin. Mathieu, you are here, okay.
Yes, I am.
And so Boris, I'll ask you to stop sharing your screen. I think I can do it for you, but if you could, yeah. Okay, perfect. Thank you, Mathieu. We can see your slide and I think we can hear you. So you're also...
Okay, great. My name is Mathieu Fortin. I'm a research scientist at the Canadian Forest Service, and more precisely in one of its branch called the Canadian Wood Fiber Centre. My field of expertise is forest biometrics. So today I want to talk about a comparison of uncertainty quantification techniques for national greenhouse gas inventories. So as you all know, most countries around the world are now part of the United Nations Framework Convention on Climate Change. And according to that convention, the countries have to report on an annual basis on their greenhouse gas emission. So that's not trivial. It takes a lot of understanding of what's going on within the country in different sectors. So in 1995, the first IPCC guidelines for those national greenhouse gas inventories were published. And since then, we have seen many versions. And the latest version is 2006, which is a complete version. And in 2019, there were some refinements that were published as well. So this is a very important source of information because it makes it possible to compare the countries and see, okay, who are the good students who managed to reduce their greenhouse gas emissions and who are the bad students. Canada is probably part of the latter, but that's another discussion. And it's also really important within a country, if you want, well, the governments are trying to implement some policies and strategies in order to reduce the greenhouse gas emissions. So if we want to know whether these strategies or policies were effective, we need some data, and those greenhouse gas inventory provide this crucial data. The problem is that greenhouse gas emissions are almost never measured directly. We always rely on sampling. Most quantities are estimated. And we estimate basic quantities, and I'm going to provide you with some examples in the next slide. But the problem is that when we multiply those estimates, obviously we get some estimate of the greenhouse gas emission, and we can wonder what is the precision of those estimated greenhouse gas emissions. Okay, if you wonder if this has been addressed by the IPCC, I'm going to go to the back one slide. There is a whole chapter in the volume 1 of the IPCC guidelines, the chapter 3 in volume 1, which is completely about uncertainty quantification. Actually, the IPCC suggests two methods for uncertainty quantification, and in this study, we came up with three. Well, I came up with 3 other methods and made a sort of comparisons between those 5 methods. So, mathematically speaking, if we have if E is the estimated emissions, alpha stands for the greenhouse gas emission per unit of area, and B stands for the area. A simple example of product of estimates in order to get estimated emissions would be that one. We would just multiply the estimated greenhouse gas emission per unit of area by the estimated area, and we would get the estimated greenhouse gas emissions. So just to make things clear, when you have a symbol without the hat, that's the true value. That's the value we don't know. And when we estimate that value, we get an estimate, we put a hat on top of the symbol. So the equation you can see on the left-hand side here, it's actually the estimated emissions which is calculated as a product of greenhouse gas emission per unit of area by estimation of the area, by estimate of the area, sorry. So the precision is measured, well, a common method to measure precision is the variance. So you all know the variance. I think you've all been fitting regression or using regression to fit some models. The variance, the larger the variance, it means that our observations are spread or the errors are greater or larger. And it means that we have a lower precision. So the other way around, if we have a lower variance, we have a very high precision. So the problem is, well, so far we don't have a problem. If we had the real quantity, okay, the real greenhouse gas emission per unit of area, the real area, we would just use that formula here and we would get the variance of our estimated greenhouse gas emission. The problem is that if you take a look at the right-hand side, all those values here are real values, the values we don't know. So basically we need a way to estimate this value here. So we need what we call in statistics an estimator of the variance. So in the next slide, I'm going to show you the 5 estimators that were tested in this study. Okay, so a first estimator would be, we would simply replace those true values here by their estimates like this. And we call this a naive estimator. So as you can see here, we just put some hats here on the different symbols to show that we're not using the real greenhouse gas emission per unit of area. Instead, we're going to use the estimate. Okay. There is a second method here, which is called the propagation-based estimator. That's actually the IPCC first method. There are 2, and so that's the first one here. You can see that the difference is just we omit here this product. And finally, if you dig a little bit in the literature, 60 years ago, it was published by Goodman. Goodman said, okay, a proper estimator for the product of 2 estimates would be this one. And the only difference is that we're going to subtract here this product of the variances, okay? So we can wonder, okay, there are 3 estimates. Which one is the best? So one way to assess the performance of an estimator, basically you want to see on average if that estimator will be, will stick to the true value of the variance, which is explained here, which is provided here. Okay, so if you do that with this, if you know that the properties of the expectation and variance, you will find out that this estimator here tends to overestimate the true variance, and the bias is twice this product of the variance here. If you look at the first IPCC method, the propagation-based estimator, you find out that again it overestimates the true variance, and the bias is slightly lower. It's actually only the product and not twice this product. And when you look at Goodman's estimator, actually it's unbiased. Okay. So that's one way to do it. As I said, there are 5 estimators that were tested in this study, and the IPCC recommend another one, which is the Monte Carlo variance estimator that you all know. Basically what we do, we just compute realizations of our estimated greenhouse gas emissions. And then we get an approximate distribution, we calculate the variance of that distribution, and we get an estimator. So that is the second method suggested by the IPCC. It turns out that through mathematical development, you can show that this method is as biased as the naive estimator. Okay, so namely the bias is again twice the product of the 2 variances. What we can do, we can rescale this Monte Carlo variance estimator here by multiplying our realization by a factor, and that factor would be based on Goodman's estimator, which is known to be unbiased. Okay, so that was the 5th method, or the 5th estimators that was tested in this study. So just to get an overview of what the magnitude of the bias, okay, here it's all expressed in a relative manner. So here the lambda stands for the relative standard error. It's similar to the coefficient of variation. Okay, so basically, if we have here the product of two estimates in order to get our estimated greenhouse gas emissions. Okay, if we use a naive variance estimator and we have like a 30% relative standard error in our alpha hat and a 30% in alpha, we stand somewhere here. We have a 10% overestimation of the variance. If we take a look at the propagation base, which is the first method suggested by the IPCC, the bias is approximately half that of the naive variance estimator. So of course, in greenhouse gas, when it comes to estimating greenhouse gas emission, it's not only the product of two estimates, it can be the product of 3, 4, or even 5 estimates. So we can use those estimators in a recursive manner so that we take into account that product. And another example here is if we have the product of 3 estimates here, okay, so we would have an additional, our product would be, for example, alpha hat times beta hat and times gamma hat. If we have a 30% standard, relative standard error in each, we are somewhere here. We have a 20% of variance overestimation here. If we use a naive variance estimator, and propagation base is approximately half this bias. So this is all done mathematically, and you can probably wonder, okay, it's all maths, it's all complicated. Is there another way to test that to make sure that we have, we really have bias? By the way, here I didn't show the Goodman's estimator because it's unbiased. Actually, if I plot it, the surface is pretty flat to 0. So another way to test those estimators is through a simulation study. So what we do is simple. We just run a simulation with different factors. We sample a population, and then we know the factors, the real values of the estimators. And again, we get the same result. If we use a naive variance estimator or the Monte Carlo estimator, we get a very large overestimation here. If we have the propagation base, it's not as bad. If we use Goodman's or rescale Monte Carlo estimator, we get an unbiased, almost unbiased variance estimator. So take-home messages: the IPCC recommend the propagation-based variance estimator and the Monte Carlo variance estimator, but they discourage the use of the propagation-based estimator in some contexts. And the reason is that it tends to underestimate the uncertainty of multiplicative terms. So that is in the IPCC. This statement is actually incorrect. As a matter of fact, the propagation base is less unbiased than the Monte Carlo variance estimator. Actually, propagation base, if you had one of these two to use, you better use a propagation base. The Monte Carlo variance estimator is the one with the largest bias. There is this misconceived idea that Monte Carlo estimators are always unbiased. That's not true. Monte Carlo estimators were designed as a last resort solution, and they should be considered as such. Is when we don't have any other possibility or option, we use a Monte Carlo estimator. Only Goodman's and the rescale Monte Carlo variance estimator can be considered as unbiased. Here in this study, we considered that the estimates that compose a product, whether there are 2, 3, or 4 estimates that compose this product, they're all independent from each other. So this example of the greenhouse gas emission per unit of area times the area is a good one. Normally, there is no dependence between these two, but however, there are some cases where those estimates can be dependent, and those Goodman estimator is not designed to deal with dependent estimates. So that's a limitation. In that case, I would strongly suggest to use a Monte Carlo, even though we can consider that it is biased. So this has been published a few months ago in Mitigation and Adaptation Strategies for Global Change, and there's an R package that implements those estimators. So if you want to use them, just get in touch with me or try to find the publication in this journal, and you will get the URL to the R package. So thank you for your attention.
Mathieu's time.
Yeah.
Thank you very much, Mathieu.
Helen, I need your advice. Because we have 10 minutes. Could we use 5 minutes after or not?
Yes, for those who want to stick around, yes. I might have to leave though to take care of the next session. So I'll try to have it recorded, but it might stop recording when I leave the room. We'll see. But yeah,
we will survive without recording.
But yeah, the next session, there is a 10-minute breaks between the two sessions. So you have like not more than 5 minutes.
That I used 10 minutes for last presentation because simply to show what I was going to discuss. And after that, we will have 5 minutes for Werner.
Yes.
Okay, share screen. Where we are here. Yeah, we have just a moment. Why it does not work?
It works. Okay, we can see your slide.
I beg your pardon, because you understand 9 minutes. I have simply to say some words. Reanalysis of carbon cycling of Russian forest. Why? There are about 35 peer-reviewed and official papers for last 5 years. And if we look what is doing in this paper, without any details, excuse me, carbon sink 10 times difference, and papers are peer-reviewed. There are outliers, but 400, 800 without outliers. That is necessary to understand what we try to do. To put question what we would like to know, what we could do, what could be called analysis, and what is new. That question is why we were able to do analysis. Probably the first time we used in-system remote sensing data, which have been received by the Institute of Space Research, Sergei Bartolov, and we produce practically or modified new system, different questions. If somebody would have an interest, it could. What is the principal point? We consider what we have to know. Account should be full and verified, and so uncertainties, it should be difference what we have and what exists in reality. Excuse me, maybe it's everybody knows that we have two background, that is change of stock and change of measurement of fluxes. One important point, carbon account is fuzzy system, abstract carbon system, and that it follows from theory. If we have underspecified or fuzzy system, we cannot estimate exactly reliable uncertainty without any evidences. That we have to use all what we could use, different methods, and try to find something from these methods. I mean that we could calculate uncertainty using Bayesian approach, but there are many questions, theoretical and practical. In order to be able to use system approach, it's necessary to have unified information base. We did that in form of integrated land information system. Why that's important? Why it was necessary to do this reanalysis? Because if you look in official data, which we have forest, we had now growing stock Russian forest 84 billion cubic meters. Shepashenko made yesterday, he said 111, and Bartolov said 105. Generally difference in 20 billion cubic meters for Russia. I believe that it's necessary to say why this 20. That's, I am missing everything because we do not have time. That's simply these pictures, that's different systems which have been developed, and beyond of this system, there are many thousand or maybe 100,000 of megabytes information. Some interesting, very important question. As a part, it's necessary to calculate all uncertainty, emission of all uncertainties. In Russia, there is clear change of fire regimes, and what our fire experts printed during last years, that is to some extent, I will say that is shock, because the last 4 years, taken into account, and this year, we had more than 10 million hectares of burnt areas that when we had fire, and about 50% of mortality. It has never been. That's as a result of integrated land interface system. We have spatially distributed with resolution 250 meters here, all indicators. And based on these materials, we calculate carbon account with so-called land ecosystem approach, like aggregation of all inventory. And we have, if we look what is doing outside of that, because I said that we have to use different methods, and after that, try to provide mutual constraints. That we have inverse modeling, we have DGVM, we have eddy covariance. Eddy covariance is not a scientific for Russia to not enough measurements. Inverse modeling generally, this is from GOSAT, but there are about 20 different results for Russia for last 5-7 years. That is something for 500 to 800. DGVM, second generation of DGVM is not applicable to North. That is at least to Northern Eurasia, because heterotrophic respiration is not good, not fit to mechanism of heterotrophic respiration, specifically on permafrost, and decrease result something 200 or 300 million ton of carbon, but NPP, very good. That is simply, but I have to say the current generation of DGVM, that is combination, I forgot some words, combination of fusion of model and data, very good results with very similar to what we have. Finally, 1 minute and yeah. If we use only layer landscape ecosystem approach, we have roughly 600 teragram carbon sink in 2016 with uncertainties roughly 25-27%, probability 0.99. Unfortunately, we have not been able to give today answer what will be if we would use a really system approach, because for 2016, we still did not find enough data, the rest of methods. But what we were able to do, that is something for 50 billion ton more, but we do not know. And, excuse me, finally, you see that this is picture preliminary, but we have very high sink, but roughly 30-40% of territory is a rather high source, and that is after fires, and that is on permafrost. I beg your pardon for this so-called presentation. I understand that no time for questions, and all we could say that this year will be a rather big amount of 3 or 5 publications of this topic, which would be possible to read. Many thanks.